All right, so where are we at? 14 what? 1417I. 1417I. Okay, all right, let's see. All right then. So what we got here is first of all, let's take a stock of where we are. We're looking at cosets. Cosets involve a subgroup, and the subgroup produces a partition of the set. And on Tuesday, I talked about how cosets are like raisin bread, and instead of like layers of the onion. But in this case, the cosets are actually like layers of the onion. So that will kind of come out. And I'm looking for my stylus, my new stylus that came today. I don't see it. I hope I didn't lose it. Well, anyway, let's do it without the stylus, and we'll see where we get. All right, so T is now this multiplicative group. So T is a subgroup of C star. It's T is all the complex numbers with modulus 1. Just recall it's a subgroup because take any two complex numbers modulus 1, you multiply them, you get another complex number of modulus 1. If you take the inverse, it's also a complex number modulus 1. So that's enough to show that it's a subgroup. All right, so now you want the cosets. Now to get a coset, to get any old coset, what you do is you take that subgroup and you multiply it by anything in the group, and that will give you a coset. So give me a coset. Well, first of all, give me a complex number to multiply by. All right, but that's okay. Well, all right, you could do that. You can do that. That's fine. If you're able to do that, that's fine. All right. So if you're going to say r cis theta, yeah, well, that's good. That's actually very good, because if it's a multiplicative problem, you typically are going to want to use polar form if you're multiplying. So that's a good choice. All right. So all right, now so you're saying multiply by r cis theta. So how would you express an arbitrary element in T? How would you express an arbitrary element in T? Because remember, what you want to do now is you want to multiply your r cis theta by every element in that in T. Yeah, cis something. Yeah, very good. Cis something. You call it something else. Cis phi. Cis phi is good. Okay. So what happens if you multiply cis phi times r cis theta? Go back to, I know it was ancient history, but you can go back to the complex numbers chapter and find out. But that really is something that you should, actually that is something that you should take away from the class, be able to multiply. Are you still there? Hello? Yeah, okay, yes. Sorry, I lost you for a second because I plugged in my tablet. But that is, multiplying polar complex numbers is something you should be able to do without having to look up. It's a very simple rule. Yeah, that's right. The rule is The rule is somewhere here. All right, yeah, here. It says, well, it even summarizes the rule somewhere here. Multiplication, multiply the two moduli and add the two arguments. And that's what you do. All right, so I found my stylus, so we can do something here. Hopefully this will come up. This is the first time I'm using it, so we'll see if it works. It's okay. Very good. All right, no, this is the wrong notebook. Let's go to another notebook. Too many notebooks. I guess we'll go here. Whoops, down here, sorry. And let's see if I have one on Cosets. Right, well, I don't, okay, let's see. Cosets. Well, this is equivalence classes. Here it says 13 is equivalence classes, but 13 is, we're on 14, okay. All right, so let's see. So let's make another one. Is there anything in here? All right, let's put it here. Okay, and just to be formal about this, let's go and look at the question, which is here, and we'll copy that. Here we go. Well, here I'll do this. I don't need to copy all of that, and then I'll copy the T. Okay. All right, there we go. All right, so let's do this. And why does it? Oh, I see. I have to go like this, I think. Why is it not? Why is it saying I can't draw? I see. So I'm going to have to install some tablet drivers. Let me use my other tablet. I suppose so. Yeah, all right, let's see if that works. Go out. And if I go here, and here, and here, and here, it still says no. That's strange. All right, well, let's take this out. So it's not liking me. That's really funny. That's never happened to me before. Well, we'll just have to type then. All right, so we'll just type. Okay. All right, so what you said was we'll take an arbitrary complex number. I should learn from Amanda. She types everything. So we'll call that r cis theta. Okay, and then we'll multiply that. Oops. Multiply by an arbitrary element of t. What was that? It just lost everything. Okay, here we go. Okay, so we'll call arbitrary element of t, we can call that, well, it's going to be cis phi. So the result is, I think somebody said, r cis theta plus phi. Okay. All right, now, remember that an arbitrary element of t is, what do we know about, so arbitrary element of t, what do we know about phi? Okay. Okay, but in particular, well, it is a real number, that's true. But you don't really have to choose anything, do you? Well, I mean, I could choose phi as anything, that's true. But I don't have to, but then I'll get some duplicates, right? Well, we can just say any real number. Well, if we can say any real number, that's fine. Okay, that's fine. Okay, now, so in this, remember we're multiplying this element, r cis theta, by everything in this set. Okay? When you take the coset, you're multiplying the subgroup, everything in the subgroup by this one number r cis theta. So here, let me put set brackets around this, because really that's what we're talking about. All right. So the result is going to be a set of numbers in the complex plane. Are you with me? Is any real number. Okay. Now, what does this set look like? What does this set look like? One still hasn't come back. All right, well, nothing I can do. Yeah, probably something to do with the circle. Why don't we take a particular example then? If you're having trouble seeing what this is, let's take a particular example. Like instead of r cis theta, why don't we take, well, let's take something simple. Of course, we could take 0. Oh, no, but 0 is not in C star, so we can't take 0. And 1 is too simple, because 1 would just give you t. So how about something like, suppose I took I. Okay, suppose I took I. All right. Then what would I get? So what is I in terms of cis? I mean, think about the unit circle. Yeah, pi over 2. That's how far you go. That's how far you go around the circle to get to I, right? You go start at 0. You go around to pi over 2. Yeah, I really got to get this. Well, never mind. All right. So, all right. So here we have, instead of theta, we have pi over 2. Okay. All right, now. And what is r? R is 1, right? So we just have cis pi. Okay. All right. Now, what is this set? First of all, what's the modulus of every element in this set? One. Its modulus is 1. Okay. So geometrically, that tells you something. All right, that means every point lies on that circle. Now, does this include every point on the circle of radius 1? Okay, how do you argue that? Yeah. Yeah, okay, because if you plug in any number for phi, basically you can get any number for pi over 2 plus phi. Okay, so this is this set. This set is the unit circle, which is equal to t. All right. Now, that shouldn't be a surprise, because if you remember, we talked about multiplication by I is the same as rotation by 90 degrees. So you can think of multiplication by I geometrically as a rotation by 90 degrees. See this pi over 2? So you've taken your unit circle and you've rotated it by 90 degrees. And you still have the same unit circle again. All right, so that's one complex number. Let's take another complex number. All right. So let's see. Let's try. All right. Let's see if that's true. Let's try 2i. Well, then I put a 2 here, right? And then I get a 2 here. And this isn't the unit circle anymore. It says the circle of radius 2. Okay, all right, let's try another one. We're going good here. So let's try another one. Let's try, let's do 1 plus I, which happens to be square root of 2. Whoops. Square root of 2. All right, I have to do this. All right, there we go. Happens to be square root of 2 cis pi over 4. You can get the square root of 2 because the 1 and the I form a right triangle with hypotenuse square root of 2, and the angle is pi over 4. All right, so what changes over here? Yeah, it's going to be. Okay, that's not square root. How did that come out? Okay. Okay, and then what else changes? Okay, right, okay. Now what about that? Okay, right, okay. Okay, whoops, sorry, I have to do this. Right, so in fact, I can get any number with radius square root of 2. Okay. So what are the cosets? Well, cosets are not numbers. Cosets are sets. And I should say the left cosets, right? Because I haven't done right cosets yet. Okay, so it's coset, left cosets. So what did the problem ask for exactly? It said, it says list left cosets. All right, so I think Amanda was asking about this. But at least we can describe them first. The left cosets of T are all circles, or all the circles. Okay. Of radius r. Well, let's see. Well, what else do you know about? Can I take any circle? For instance, could I take a circle whose center is at 1? Would that be a coset? It's very frustrating. I can't draw, but it's still doing this. I'll tell you what. Let me close out of this and open it again and see if it will let me open it. Okay, let's see if it works now. Or if it remembers me. Oh, very good, it's there. All right. So I will do something else. Let's try this. This time it should work. All right, yes, and it didn't go out on me. But it's not working. All right, let's try this. What's going on? It doesn't like me today. I guess my battery's out or something. Oh, there we go. I got it. Okay. All right. So, what we did so far, right? We had the unit circle. Let me do it down here. We had the unit circle with radius 1, and then one of the cosets was the same thing. Another coset was the circle radius 2. And then we had another coset with circle radius square root of 2, which is here. All right. All right. So, for instance, is this a coset? I mean, it's a circle, right? Is this a coset? Why? Okay. All right, this is divine inspiration. Well, the thing is that certainly elements of this circle are in cosets, but they're not all in the same coset. I mean, there's a very good reason to say immediately that it's not a coset. What do you know about cosets? Well, these aren't the same size. All right. Well, I see what you're saying. I mean, these are all the same size because they have infinite elements, infinite number of elements. So same size means same number of elements. So these are all infinite. So that's not a problem. But there's another reason. What do you know about how cosets sit inside the big set? It's the P word. The P word. In fact, it's the whole reason why we had chapter 13. Partition. Cosets are a partition of the group. Now, what do you know about partitions? Partitions consist of sets. What about those sets? Okay. All right. Well, remember when we talked about... No, and when we talked in chapter 13, we didn't mention groups at all. There's no mention of groups whatsoever. Yes. Yes, subsets, not subgroups. Subsets. Now, all right. So the partition splits up the set into subsets. But what about those subsets? They're pairwise disjoint. They're disjoint, right? So this cannot be a coset because it's not disjoint. It intersects this red one and this green one. Can't possibly be a coset. All right, so I need to finish this statement here, which I haven't finished yet. I'll have to move it down. Now, what about the circles? So I can't be any circle. All right, what did you say? What did you say, Adam? Centered at 0. Okay. So all the circles radius is centered at 0. Now, technically, a circle can have radius 0. Does this include the circles of radius 0? That's correct. Yes, it's not. So with radius greater than 0. All right, so that's this. Now I remember that somebody, I think it was Amanda, had a question. How do you list these? Well, that was a nice musical introduction. Okay. So all right. So let me call the set of course. Let's call it C. It's bigger than I wanted to make it. So if I want to list these cosets, let's see. Let me call S. What we can call C. Okay. Now, they're all the circles. So each circle has a radius, right? All right. So then you'd have to. You could say that. Yes, you could say, but it's a set, right? Whoops. Sorry, I have to do this. Then it says for all R greater than 0. Okay, so each one of these, for any particular R, this is a set. And then to get all the cosets, I just have to take this. I have to take these sets for all R greater than 0. Now you can also say something like this. I could say something like this. I could say C equals TR, just abbreviate that. T sub R, like this, where T sub R is the circle of radius R centered at 0. You could say that either way. Okay, let's see. What is it? Yeah, it could be. It could have asked for the size. Whoops. For 14,210H. Well, yeah. Is that if it's using that absolute value? Why is it? Well, it's the number of cosets, yes. All right, so we didn't answer the question though. How many? So this was the left cosets. What about right cosets? Okay. Well, that's not the reason. are the same because, well, the difference between left and right coset is left you multiply on the left and right you multiply on the right. Now, why doesn't it make any difference whether you multiply on the left or right? Okay? Because, alright, because C star, whoops, not C8, C star is commutative. And I could be even more specific if you want, so it doesn't matter if you multiply on the left or on the right. You could say that. All right. Well, it's good we went through this in detail. I mean, you certainly don't have to go through as much detail with the others. But I think this does illustrate some good features that the cosets do. I mean, some things about complex numbers that are quite key here. That multiplication by complex numbers is a combination of rotation and stretching. So if you take a circle centered at the origin and you rotate it, it's still a circle. And if you stretch it, it's still a circle, but it has different radius. The other thing that I want to point out is that out of all these cosets, which ones are groups? Yes, this one in particular, yes. Only the black one. How many of them have the identity? Yeah, you can't have there's only one coset that has the identity, and the cosets are disjoint. So I think I guess I'm talking to Adam in particular. Make sure you make sure when think about whether something is a subset or a subgroup. Those are completely different things. Subgroup is a much stronger condition than subset. So subsets are subgroups, but subgroups are subsets, but most subsets are not subgroups. Okay, all right, very good. I think that was quite instructive, and I think that all you guys listening to the video, you should thank these people. Yes, go ahead. Let's see. This one is due when? It's due to tomorrow. I'm going to have a short assignment because I want to finish up this chapter. We should, because we do need to finish up cosets. I think we only made it through fourth. We started 4. We just barely started 4, but we. I didn't say. Somebody else said. Is it due tonight? I guess that means that somebody wants it to be due later. Okay. All right. Well, should I look and see what it is actually? Okay. All right. Let me see. I don't believe you. Let me see. Okay, that's fine. All right, that's fine. All right, it's coming up slowly. And which one is it? No, it's not. No, that's undergraduate. Let's see. Assignments. What does it say? Let's see. Okay, yes. So Let me make sure what it says. Well, what do you know? It says Sunday. So you can tell Jesse that he was wrong. Okay, but I do want to have one more, and we'll do the test the same way as the midterm is. It's basically take home on the honor system, 3 hour take home. The reason I do it that way is that the comprehensive exams are like that. I mean, the comprehensive exams are 3 hours, so it's good practice. And comprehensive is also 50% is passive. The way we've been saying is that if you make 2 conference presentations, then that substitutes. Or if you write a paper and publish a paper. Yeah, that's true. I think the actuary. I have to talk to Minnie about that if we're going to maintain that. That was when we were thinking of an actuary focus, but we really don't have an actuary focus anymore. I'll have to talk to Minnie about that. Is that something you'd be interested in? It's just it's 100 and something, right? Well, yeah. I mean, if you're not thinking of becoming an actuary, yeah, that's yes. Well, you can take it again. I mean, that one you can take as many times. I think you can take it any time. I don't know if you have to wait between times you take it. Maybe you have to wait a couple weeks or something. Yeah, you do. Yes, that's true. That's true. All right. So we did that. So what else do you want to talk about? Okay. Okay. Yes. Yes. So now, all right. So one way is easy. One way should be easy. So, okay. Okay. Maybe a robocall. Oh, sure, okay, I'll unshare. Alright, so I've stopped. 1423. Oh, I see it. Okay, yes, okay. Oh, yes, very good. All right, so you're saying you need to show that the left-hand side is containing the right-hand side, and the right-hand side is containing the left-hand side. All right, now you should be a little bit more clear to say when which one are you proving first? You put suppose G is in G, so which one are you proving first? Well, all right, I guess it's okay to do that, but just put it on a second line. Okay, so you're saying suppose G is in big G, then okay. But it's not arbitrary. It's not arbitrary at all. If you've chosen little g, then GH is strictly determined, exactly determined. It's not arbitrary at all. Right? So that's fine. You can say G is in GH. Why is it, well, maybe you should, just to make clear, why is G in GH? All right, well, let's think about it. You don't need the rule. You could probably use the rule, but you don't need the rule. What does GH mean? All right, but what's the definition? You're multiplying little g by what? So what does it mean to multiply a set, by an element, by a subgroup? I mean, we just saw that the result is a set. The result is a set. So what it means is that I multiply little g by every single element in big H. So I take all the elements in big H and multiply them one by one with little g. And the resulting elements are GH. So why is little g an element of GH? Because, yes, very good. That's a very key point. Since the identity is in H, then GE is in GH. That's the key point. All right, so that's where I would say there that you can't say arbitrary coset. You say G is in GH because you can say because G equals GE. And then you can, then the next line is fine. All right, now how about the other way? How about showing that the union of cosets is, right? All right, well, you have a union of sets is a subset of some set. You have a union of sets is a subset of some set. So to show that it's a subset, you have to show that everything in the union is in big G. All right. Now, since it's now, you can look at those sets in the union one by one, right? If every one of those sets is in big G, then the union's in big G. All right, so you can approach it that way. Think about it that way.